There's no going back from this, James Webb Telescope uncovers. A year ago, the renowned American physicist Michio Kaku made a striking statement. The James Webb Space Telescope is completely shaking up our understanding of the cosmos. Suddenly, it seems that we might have to rewrite every textbook on the origins of the universe. Traditionally, astronomers believed that creating a galaxy like the Milky Way with its 100 billion stars would take many billions of years. Yet Webb has now identified 6 galaxies that existed just half a billion years after the Big Bang. Galaxies that, in some cases, are up to 10 times larger than the Milky Way. According to our current models, such massive primordial galaxies should not exist at such an early stage of cosmic history. Clearly, something doesn't add up, and our theories about how the universe formed may need a major overhaul. More than 2 years after its successful launch, the James Webb Space Telescope has ushered in a golden age of discovery, pushing the boundaries of what humanity can observe. But these discoveries have also opened a Pandora's box of puzzles for cosmologists. Recently, Webb has once again probed the universe's first 500 million years, and what it found defies expectations. These early galaxies are anything but infantile. They are massive, mature, and far more developed than previously thought possible at such an early epoch. Among them is a galaxy that could be one of the oldest ever observed, and what's truly shocking is that it already contains billions of stars. Interestingly, just 2 years ago, the Hubble Space Telescope had spotted this cosmic giant, but only as a tiny, unusual point of light. No one could have imagined that this faint speck was actually a colossal galaxy lurking at the edge of time. It was only when Webb turned its gaze toward it that the galaxy's true nature was revealed. Now officially named GZ9P3, this galaxy exists at a redshift of Z equals 9.3, meaning we are seeing it as it was just 510 million years after the Big Bang. While astronomers have observed other galaxies as early as 350 million years post-Big Bang, none match GZ9P3 in sheer mass. This suggests that the stars within it must have formed much more rapidly and efficiently than previously believed in order for the galaxy to reach its enormous size so early. But the surprises don't end there. GZ9P3 has a peculiar structure, with 2 bright regions indicating dense galactic nuclei. This almost certainly points to a galactic merger, 2 primordial galaxies colliding in the infant universe. Beyond its age, mass, and shape, astronomers also examined its stellar population, discovering that bright, young stars dominate the galaxy's appearance. Using Webb, they detected specific elements such as silicon, carbon, and iron in its older stars. Iron, being the heaviest element that stars can forge before exploding, reveals that ancient stars had already lived and died, enriching the early universe with metals. When these stars exploded, they scattered these elements across space, enriching the early universe with metals that would later become part of new generations of stars. Surprisingly, astronomers also found that GZ9P3 contains more old stars than initially expected. This indicates that galaxies may have reached chemical maturity far more quickly than previously assumed, with stars enriching the universe with metals at a faster rate than models had predicted. The unexpectedly mature population of older stars in GZ9P3 challenges our current understanding, suggesting that star formation began much earlier than we once thought, and that these stars had already aged significantly by this epoch. These observations imply that a new theoretical framework may be necessary to explain how galaxies could grow so rapidly to reach such chemically mature states. Beyond their sheer size, these findings also hint that galactic mergers may have been a dominant force shaping the universe immediately after the Big Bang. Our current cosmological framework may not be fundamentally wrong, but it seems that our perception of the speed of galaxy formation requires adjustment, especially given that these galaxies are far more massive than previously considered possible. Even though our cosmological model has been meticulously built upon observations, theoretical constructs, and supporting mathematics, there remain subtle discrepancies suggesting that the universe isn't adding up perfectly. You may have heard of the so-called crisis in cosmology. Essentially, this crisis began when different methods for measuring the universe's age began producing conflicting results, a situation that persists to this day, and one that cosmologists still struggle to explain. Recent discoveries from the James Webb Space Telescope have only deepened this conundrum. The universe is expanding, with distant galaxies moving ever farther away from us. If we calculate the rate of this expansion using the cosmic microwave background, the faint light left over from when the universe was only 380,000 years old, we get one value. Another method uses distant supernovae, comparing their expected brightness to how bright they appear from Earth. This technique, known as standard candles, allows scientists to estimate the universe's expansion rate at the time of the supernova. The expansion rate measured this way, known as the Hubble constant, differs from the rate derived from the cosmic microwave background. This discrepancy between the two methods is called the Hubble tension, and it lies at the heart of the crisis in cosmology. But the Hubble tension is no longer the only problem. A new form of cosmological tension has emerged, challenging our models in unprecedented ways. I've spent my life developing this particular theory of the universe, and now that theory is being questioned. But that is exactly how science progresses, by confronting the unknown and rethinking assumptions. When you look up at the night sky, assuming you're away from city lights, you see countless stars. You may even spot the Andromeda Galaxy as a faint smudge among them. That's because the universe is densely populated with stars and galaxies. But here's the question: how much of the universe do they actually fill? In other words, how much matter truly exists? This might seem like a simple question, but the answer is anything but straightforward. The dilemma arises because current cosmological observations disagree on how matter is distributed in the universe today. This disagreement has given rise to the mysterious S8 tension, also known as the new cosmological distress. The S8 tension measures the lumpiness or clustering of matter in the cosmos. To visualize it, imagine the universe as a colossal puzzle with pieces of matter scattered throughout space. Scientists aim to understand how this matter is distributed and how it clusters together over time. Astronomers often study the distribution of matter in the universe using low redshift observations such as weak gravitational lensing. Gravitational lensing occurs when the immense gravitational pull of massive objects like black holes or galaxies bends and distorts the light from more distant sources. This effect acts like a cosmic magnifying glass, revealing details that would otherwise remain invisible, offering unique insights into the large-scale structure of the cosmos. However, a puzzling discrepancy arises when comparing these observations with predictions from the Standard Model of Cosmology, which relies on measurements from the cosmic microwave background. The S8 value used to quantify the lumpiness or clustering of matter in the cosmos, derived from these two methods, does not match. This mismatch lies at the heart of the so-called S8 tension. Clearly, something fundamental is missing from our understanding. Despite decades of theories, observations, and hypothetical constructs supporting those theories, the universe continues to challenge us. To probe this mystery further, astronomers turned to one of the most powerful supercomputers in the world to run the largest cosmological simulations ever attempted. The scale of the project is staggering. The simulations required more than 50 million hours of computing time across 30,000 processors at the Durham-Dirac COSMA 8 supercomputer in the UK. The project, known as Flamingo, an acronym for Full Hydro Large-Scale Structure Simulations with All-Sky Mapping for the Interpretation of Next-Generation Observations, sets itself apart from earlier simulations by the sheer size, high resolution, and the inclusion of more than just gravity. Until now, most cosmological simulations focused almost exclusively on dark matter, since it constitutes the majority of matter in the universe. Yet ordinary baryonic matter, although making up only about a 25th of the universe's total mass, plays a significant role in shaping cosmic structures at smaller scales. For instance, galactic winds powered by supermassive black holes or supernova explosions can slow or even halt galaxy growth. Unlike previous models, Flamingo tracks both dark matter and